Nick Duda.
Oh, thank you, Fred. So I'm happy to be here today. I want to thank Fred for that introduction. It reminds me of days long gone by. I know when I first was invited, when Fred asked me to come here, I wasn't exactly sure what he had in mind for me to talk about, because I'll start right out front and say that I really know very, very little about speech recognition. I know absolutely nothing about language engineering. I have been working the last several years on sound output, spatial sound. That's what I'll be talking about today. Might as well see if this works and get the title slide on. I was reminded of Admiral Stockbridge's surprise statement 4 years ago at a political convention when he got up and said, surprised everybody by saying, "Who am I? What am I doing here?" And I feel a little bit like that. The who am I? Well, I've been working in a lot of different areas, in statistical pattern recognition, in some expert systems things. I worked with Dick Lyon on some auditory scene analysis, which is more relevant to what you people do. I decided several years ago that the problems you people are all doing are much too hard, and I wanted to pick a much easier problem. And spatial sound seemed like a very interesting and relatively easy problem, and I think it is both interesting and relatively easy, and yet there are some difficulties in it. And what I'd like to do today is to kind of give you an overview of techniques used for synthesizing spatial sound, the way we're approaching it, developing models based on the physics of the way sound propagates and diffracts and so on, and to point out what some of the remaining problems are, the research areas that are still presenting us with some challenges. So what I will do is talk briefly about this. This is an overview of some basic ideas on the physics of how sound waves interact with the body, some psychoacoustics on what kinds of cues do we pick up on to find out where sounds are coming from. I'll mostly be talking about head-related transfer functions. I know some people in the audience did PhD theses in this area, so there's some familiarity with it. I'll be talking a lot about simple models, almost embarrassingly simple, and yet they do, I think, capture a lot of the main phenomena that are involved. And then I'll talk about conclusions. I know I'm supposed to have until noon, is that right? Or,
Well, but you don't have to use the line.
well, my usual problem is that I run over. And so around 2 p.m. people get tired and they want to have lunch. So if I do run over, I thought one way to handle it is to go right to the conclusions, so I don't get past that. Basic conclusions I want you to come away with are that these head-related transfer functions do capture the physical cues for sound localization, the acoustic cues. There are other cues, there are visual cues and so on, but the acoustic cues are in the HRTFs. They can be used to synthesize quite convincing spatial sound. These models I'll talk about, these structural models, do explain the basic phenomena. It looks complicated, but it's not that complicated. The major components of the model account for the effects of the head, the outer ears, the pinna, and the torso on the sound. And the nice thing about the structural models is that they can be adapted to individuals. One of the whole problems with HRTFs is that they are different for every person. That the differences may seem small, but they can have big effects on, for example, confusion between is the sound in front of me or behind me. Okay? It's kind of like eyeglasses. You can't use the same glasses for everybody. You can't use the same HRTFs for everybody. If you try to do it, you'll introduce these kinds of errors. So the models that I'll talk about are models that we can either take HRTF data or anthropometric measurements of the body and fit the models, and I think that's a big advantage. We have fine models for the head and torso. That's not a big deal. Problem remains the outer ears. The pinna are still a source of difficulty. So you can leave now if you're not interested in any of this, because you've heard what I'm going to do. People stayed, good. Okay. Here's Physics 1A on sound propagation. We all know that If you have sound going through the air, it travels at a fixed speed, around 343 meters per second, or in English units, about a foot per millisecond, which is a nice round number. If it's a sine wave with some frequency f, then there will be a wavelength that goes along with that in the standard formula, c equals f lambda. A couple numbers to keep in mind. At the speed of a foot per millisecond, it means it's about a millisecond for the sound wave to, everything I say will go past your head in a millisecond, right? The frequency wavelength relationship at a wavelength of 1 foot, the frequency is about a kilohertz, okay? So a kilohertz is the frequency nicely in the middle of the 20 to 20 kilohertz audible range, middle on a log scale. 1 kilohertz is about the size of the head, so that's a dividing line. Things below a kilohertz are definitely in the low frequency, long wavelength region. Things above a kilohertz move into the high frequency, short wavelength region. And of course, sound never comes directly to you. Now, of course, what I'm saying is coming to you already from speakers somewhere, right here. If I turn this off, you get a quite different sound. Sound always comes from multiple paths. Reflections off the major environmental surfaces, even out of doors, there's a major reflection off the ground that we are used to. You get, if you have objects in between that are blocking the sound, well, the sound waves refract or bend around the objects. And if you have irregular surfaces, you get scattering. And of course, irregularity is wavelength dependent, right? Every surface is rough if you get to a short enough wavelength. So all these chairs in here are scattering sound at wavelengths, frequencies of a couple of kilohertz or above. If you don't think these things are important, just walk into an anechoic chamber. I'm sure some of you, how many people have been inside an anechoic chamber? Okay, about half the group. Remember the first time you walked into an anechoic chamber? It is weird. It is strange. You walk into this room with no echoes. I felt like there was a pressure on my ears. It was just a bizarre experience. Now you get used to it after a while, not to hear. But we're so used to hearing reverberation, it's surprising when you don't. Because multipath transmission is so common, and so much of a common experience, it's important to understand what it does to the spectrum. And here's, again, a very simple multipath model. Here we're saying that we have some signal source, x of t, comes to the ear by 2 paths. It can either come straight through with no change, or come on a second path where we attenuate it by some scale factor rho, a reflection coefficient, and we delay it some delta t and then add that in. So the impulse response that goes along with that would be an initial impulse and then followed delta t seconds later by rho times an impulse. And that very simple model explains a lot. For one thing, you see at low frequencies, if you go to very low frequencies, that time delay doesn't matter, DC, right? At constant frequency, you just get 1 plus rho. So that reflection added to the signal. And that's true when you're listening in a room. The reflected sound that comes off the walls and so on adds to the loudness level that you receive. However, if you go up in frequency, at some point, this time delay will delay you half a cycle. So then, instead of adding and building up the sound, it actually interferes, and you get a reduction in the sound. And so you have 1 minus rho instead of 1 plus rho. If the reflection coefficient is large, that puts a big notch in the spectrum. The spectrum that you get is a familiar comb filter one. Now, you speech people know all about this from modulation. The main point is that at a frequency of 1/1/2 of that reciprocal time delay, you get this big dip in the spectrum, and then at odd multiples it gets repeated. So this kind of a rippling pattern runs through the transfer function. And you'll see those patterns frequently in head-related transfer function data, because in addition to getting sounds scattered and reflected off of environmental surfaces, sounds are scattered and reflected off your own body, right? And that affects what gets to your ear. Questions? Yes? No, this is not a perfect sinusoid. We could get the shape of it, but it just looks roughly sinusoidal. We could work out the formula a bit. Okay. Okay, so there's really basic pictures of the sound propagation. Let's look at the psychoacoustics a little bit, because that's been studied a long time. Here's a view looking down on top of the head, and we're looking at the right-left dimension here. Have an azimuth angle theta. It's been known for over 100 years that the two basic primary cues for localizing a source in azimuth are the interaural time difference and the interaural level difference. And they come from a simple geometrical picture. Obviously, a sound wave coming was going to reach, in this case, the right ear before it reaches the left ear. It's easy to calculate what that time delay is. And it ranges, typically from, well, the sound source is straight ahead, it's 0, of course. Off to the side, it can be in the order of 7/10 of a millisecond. That's a typical type of number of an interaural time delay. We are very sensitive to these small interaural time delays. If you have a sound source right in the center and then you displace it by a small angle, and you have a person in an anechoic chamber not being confused by echoes and so on, and you ask, what's the smallest shift in angle that at a 70% level of judging you can tell? And it turns out to be about 1/2 degree. And if you ask, what does 1/2 degree amount to in terms of time delay? What's that ITD? It turns out to be something on the order of 10 microseconds. Okay? Now, if you buy a CD sampled at 44.1 kilohertz, that's 22 microseconds. So we're sensitive to 1/2 sample difference in time. Normally, we can't locate sources to anything like 1/2 degree. There's much more, and because of the confusions of interfering noises and echoes. But still, we have in our neural circuitry the ability to resolve times that small. Quite remarkable considering you're talking about neurons working at millisecond firing rates, right? So they can do 10 microsecond discriminations. Oh, the interaural level difference. That comes from the fact that obviously if the sound is reaching the far ear, this ear would be the ipsilateral ear in the same side as the sound. Here's the contralateral ear. On the contralateral side, the sound has to propagate around the head, and now that will be wavelength dependent. If you're talking long wavelengths, low frequencies, the head doesn't really do much to the sound field. That wave propagates through as if the head was not there. Right? So you don't get much of a difference in loudness or level at the two ears. However, once you get above that kilohertz range, the head is beginning to look like a blocking thing, and you cast an acoustic shadow. You get a head shadowing. So the contralateral ear is over on the shadowed side. So at higher frequencies, the sound level drops off. Curiously enough, this shadowing of the head was a big source of debate in the 19th century, shadowing in general, because you set up the wave equation and you solve the wave equation for what happens for, let's say, a sphere, which is what Rayleigh did. You discover that in the very back of the object, in the back of the sphere over here, you get what's called a bright spot, and it actually gets strong again. So in the back of the head where you expect the darkest shadow to be, you get a bright point. And people wondered whether or not that was really true, or was that some kind of Gibbs phenomenon or mathematical thing. We'll see about that. See, I managed to lose a slide here. That was azimuth. I was going to talk about elevation. Well, here it is. Elevation. We have 3 dimensions of sound in spherical coordinates: azimuth, elevation, and range, right? Those are the natural coordinates to use. The cues for elevation are much weaker, and in fact, still in some debate. We're still learning about the sources of elevation cues. About 30 years ago, people realized, mostly the work of Bateau and others, that the pinna, your outer ear, was a major source of information about the elevation of a sound source. If you look at your ears, you see, of course, all these little folds and cavities and ridges and things. And basically, your ear is like an antenna that's collecting more acoustic energy, right, funneling it into the ear canal. But by building up that energy at some frequencies, it actually results in this multipath thing with destructive effects at other frequencies. You get interference patterns, and that these are elevation dependent. If you move the source, you change the frequencies. Yes?
How much gain
How much gain do
do we have?
we have? We can get as much as 20 dB at some frequencies. You pay for that gain. As a gain bandwidth product, you're going to lose gain at some other frequencies. And the key point is that those frequencies where you lose will change with the elevation angle. So that gives you a good cue. There are resonances that occur in there. The degree to which those resonant modes are excited are cues to the elevation. Those are monaural cues. They're very different from the ITD and the ILD for azimuth, because for azimuth you have basically cues that are independent of the source spectrum, provided the spectrum is reasonably broad. If you have a sine wave, if I play a sine wave tone, boop, that's the hardest sound to localize. You don't have enough spectral information. But give a reasonably broadband sound, speech is broadband enough, you can localize quite reasonably. But if you're dealing with pinna reflections and monaural cues, now you have a deconvolution, a blind deconvolution problem. You've got the spectrum at your ear that's the product of the transfer function and the source, and you've got to figure out which of these spectral features is due to the source and which is due to the ear. That's part of the reason we're not as good at judging elevation as we are at judging azimuth. There are other cues that are less well understood. There's some that my colleagues, I've been working with Ralph Algazi at UC Davis on these problems and Carlos Avendano. We recently did quite a study of torso and shoulder reflections and discovered you get a good low frequency elevation cue from these torso reflections, but you don't get it in the median plane. You get it off on the sides. So you can judge elevation even though the spectrum is limited to below 3 kilohertz. You can get pretty good elevation judgment. And that's really nice because it is a binaural cue. It depends on differences between the left and right. Yes?
Your clothes will matter there too.
I'm sorry?
What clothes you wear.
What's the effect of the clothing you wear? Right. Obviously, if you put on a big hat, you're going to have quite an effect on the spectrum. And now here's another point, which I guess I should have mentioned at the beginning. These head-related transfer functions I'm just about to define formally. It's easy to overestimate them and think they tell the whole story. Humans are remarkably adaptive and plastic. You do something to change the spectrum radically, and after a few seconds, you adapt to it. So clothing is going to absorb some high frequencies. Basically, that's what it's going to do. It's going to tilt the spectrum. How about hair? You know, what does my beard do? Answer is relatively little. Clothing, relatively little effect. But it will tilt the spectrum, and people adapt to that. Even with the altered spectrum due to clothing, the derivatives, the changes that will occur will still show through. Right? So that's what we pick up on. I'm not going to say a lot about range. I won't say anything about that. I can't count my slides. Here we are. Range is the third dimension. I'm actually very interested in it. Today, I'm not going to go into it in any detail, but I'd just like to point out some of the basic things that are known. If you're trying to judge how far away a sound source is, the loudness is an obvious cue that there's a 1 over r fall off in amplitude, 1 over r squared in energy. And so that's 6 dB every time you double the distance, right? And that's if you know the source, if you know it's a person speaking, if you know the way they are speaking, are they speaking in a quiet voice? Are they shouting at you? If you know the production, then just the loudness is a good cue as to how far away the source is. But it's by no means the only one. Otherwise, if you had a radio, turn the volume up and down, it would sound like it's getting near and far. It doesn't do that at all. Right? If a source is very close to you, if you have a source right next to one ear, the person whispering in your ear or an insect buzzing in your ear, then you get a much bigger interaural level difference because the 1 over r, the distance is so much closer, right, here and here. So you get an interaural level difference that's much larger than the HRTFs at long range, and so that's a strong cue for things that are less than a meter away. For things that are far away, the most important cue is the ratio of the loudness of the sound that reaches your ear directly to the subsequent sound that comes in from reverberation. And you don't have to get very far away. After about a meter, it's already the case that the sound you capture in that solid angle going to the ear directly from the source becomes much less than the sound you're getting bounced off the environmental surface. Another strange experience of being in an anechoic chamber. If you walk into one, someone talks, they sound like they're much quieter than they should be. Everything is subdued. Well, you're not getting all those echoes that you're used to getting. Okay, let me get a little bit more mathematical. I want to give a proper definition of a head-related transfer function. So here I'm picturing a spherical source, distance r away from the head. The sphere is of radius r sub 0, and this thing is radiating sound waves out in a uniform way. X of f is the Fourier transform of the spectrum at the surface of the sphere. Okay? If you took the person and removed the person from the room, and you're in free space now, no echoes, then the sound that gets to where the center of the head would be, obviously there'll be a 1 over r reduction in amplitude, and there'll be a time delay, and that's all there is. All that happens in this propagation is the 1 over r and the delta t. And if you talk about that in the frequency domain, you say, oh, that's simple. There's a transfer function, h sub ff here, the free field transfer function, from the source to the point in the center of the head. And that free field transfer function has an amplitude, which is the 1 over r, and it has a phase, linear phase term here for propagation delay. Right? K is the wave number. If you put a person into the sound field, then that disturbs the sound field. Right? Things reflect and scatter off the subject. And so now we have a new situation. We now have a signal that reaches the ear canal on the left and the right. So x sub L and x sub R are the Fourier transforms of the signal at the left and right ears. We'll have a transfer function from the source to the left and right ears, and in general they're different. Well, if you're looking right at the source, and if you were perfectly symmetric, then they're the same. But in general, you have a different left ear and right ear transfer function. You might think that the transfer function will be defined as the ratio of the spectrum at the ear to the source, but no, there's good reason not to do that. Instead, we define the head-related transfer function relative to free field. We say that the spectrum at the left ear is the left ear transfer function times what would be at the center of the head in free field. And the reason it's defined that way is it now gives you a result that's independent of how far away the source was. You get rid of that 1 over r in the propagation delay. And if you want to put the source back in, it's easy, right? You just say, well, this free field is just the 1 over r e to the minus j k r times the source. So you can toss that in. Okay. If you look at this head-related transfer function for the two ears, that really does capture the acoustic cues that are produced by the presence of the body. It's information in the magnitude and in the phase. All the monaural cues, like those pinna monaural cues, can be seen from the magnitude spectrum. The time delays, the ITD and so forth, can come out of the phase. In general, these are pretty complicated functions, HL and HR. They're functions of three spatial coordinates, azimuth, elevation, and range, functions of frequency, and they depend upon the geometrical shape of the person, right? Particularly of the ears. So we want to understand those and see how we can model them. You can also look in the time domain. Most psychologists do not like to look in the time domain, and for very good reasons. You can do amazing things to waveforms in the time domain, and they're inaudible. It's basically, almost any all-pass filter that doesn't, well, anything that doesn't affect more than a few milliseconds of time has almost no effect on what you hear. So psychologists tend to stay away from looking at impulse responses. On the other hand, there are good physical reasons for wanting to look at impulse responses. They show you things about the structures that are causing the spectrum. So in the same way that we have a transfer function, we have an impulse response. If you had an impulse sound source, you could look at what impulse response you get at the two ears. It's equally characterizes things, of course. We just have a convolution with an, I'll call these things HRIR. So HRTFs for the frequency domain, HRIR for a head-related impulse response. And in fact, the HRIRs are exactly what you need for any real-time synthesis. If you look at any of the commercial products, I'll bet that most of you have a computer, maybe not here in the lab, but at home, that has a soundboard on it that you can use with games that have 3D sound, right? And if you use them, you're using something that has an HRTF built into it. They're pretty good at creating sounds that go quite a far distance outside the range of the speakers. If you have your left and right speaker next to your monitor, you can get sounds well out to the sides from these HRTF systems. They're not so red hot about up and down and front and back, but they're good on azimuth. So how these systems all work is, well, the commercial systems anyway, they have a built-in table. They have tables of HRTFs experimentally measured on one person. Okay? They got one subject experimentally measured for usually about 15-degree or 18-degree intervals in space, have them in a big table. When you want to create a sound that appears to come off from up there someplace, what you do is you take the azimuth, elevation, and range. Well, actually, in most of the systems, they use only azimuth. You look up in your table the HRTF that goes along with that. Actually, you look up the impulse response. So you get the left and right impulse responses, then you just do a real-time convolution with the source. And if that sound is supposed to move around, you just move around and interpolate in those tables, and that's how they work. Okay? What I want to do, among other things, is to replace those tables with simple models. I want to say, look, we can take our sound signal and run it through some blocks here that represent the effects of the various parts of the body. The effects of the head and the torso and the pinna, maybe even effects of the room. You want to toss a room model in. So we want to filter the sounds and produce that same result. And there are several advantages, I think, for doing this. Number one advantage is we'll be able to adjust the parameters in these models for you. Right? We get a customized or individualized HRTF by adjusting the model. There are other reasons, and from a scientific basis, the nice thing is that by breaking it down this way, you get some understanding as to what's controlling spatial sound that you do not get by just recording HRTFs and stuffing them into a table. I'll show this very briefly. We've been building databases. We have about 60 people at the moment. It's a small database, but the 60 people represent quite a range of sizes and shapes. And among other things, we make standard measurements of various dimensions on the body with quite a few measurements around the pinna. Our goal, our dream, is that I take a photograph of you, measure these dimensions, and then use that to set the parameters of the model. You've got, presto, your HRTF. There's another way which is very exciting, and I'm involved with some people at the University of Maryland in doing this. We're just starting out on a project where we want to use numerical methods to compute HRTFs, okay, which is certainly doable. It's already been done. In fact, we have still things to solve. But the idea is if you can get some kind of a 3D scanner and digitize the surface is all you really need. You don't need more than that. The impedance difference between skin and air is so great that internal structures don't matter. If you have a good surface map, then you can solve the wave equation numerically. Boundary element methods are the favorite way. And then you can calculate these HRTFs rather than measuring them experimentally. So here's an alternative. You could get your HRTF the tables if you want, if you have yourself a scanner like this.
Does this mean that you want to construct sound which will go through earphones that will sound to the person as it sounds to him otherwise?
That's exactly right.
And if he's stupidly built, then you're going to try to give him stupid sound, right?
We're going to try to match what he's used to hearing.
Which interferes.
Yeah. Look, we want to match what that person is used to hearing. If you have a large head, if you have ears that are tilted back at a certain angle, when a sound is over here, it has a certain spectrum, it should sound a certain way. If you listen to that same sound through a different HRTF, you'll get confused. It will smear out the image, throw it out of sort of sharp focus. It might think it's behind you instead of in front of you or inside your head, all kinds of wrong perceptions.
Surprise him and create a sound which will sound to him the way it would to a great ear?
Well, that's an interesting thought. There was actually a conjecture a few years ago. Fred Whiteman did some very pioneering work at the University of Wisconsin. And they found some individuals were much better than others at locating sounds. Some people are terrible, by the way. I'll say right now, I am not a very good subject. I don't participate in many of our own experiments because I have a hard time with elevation. Other people are remarkably good at it. And there was a conjecture that if, gee, maybe they have ears that are shaped in such a way that they're picking up cues that you're not. And if you heard it through that, you would now have much better, like getting glasses that focus better, right? And although there is some learning you can do, if I were to train you over a period of time, you might be able to pick up on that. Basically, it's best to have an HRTF that matches you. Well, when we do our experiments, we do a lot of things with acoustically measured HRTFs, not numerically computed. And one of our favorite subjects, and it's been used by a lot of other labs, is a dummy named KEMAR. KEMAR has been used in hearing aid research. How many people have heard of KEMAR? But again, half the audience probably. Well, not so many. Okay. KEMAR stands for Knowles Electronic Mannequin for Acoustic or Auditory Research. And as I say, it was originally designed for people designing hearing aids so they could put filters in that would recreate the spectrum when the microphone is at some other spot on the body. And so KEMAR has this nice feature. You can take the top of his head off and you can put little there are microphones installed so you can measure what actually comes in. There's even a Zwislocki coupler that models the ear canal and the eardrum impedance and everything. So that works out well. What happens when you do that, when you measure, let's say, an impulse response from KEMAR? Here is actually a result. One of thousands, tens of thousands of measurements we have. Here's a KEMAR impulse response. In this case, the azimuth is -45, so it's over on the left, right? And elevation 0. So what do you see? You see at the left ear this interesting impulse response, and at the right ear another one. And what do you learn from that? A couple obvious things. First, when the left ear response is much bigger than the right ear, sure, that's the interaural level difference, right? There it is. The left ear comes before the right ear. There's the interaural time difference. So the two best known cues are also obvious when you just look at the impulse responses. But the next thing you notice is that there's just a lot of wiggling going on here, right? At the beginning, there's sort of like a little precursor, and then this big impulse builds up, and then even a bigger negative overshoot. What's causing that? Why do we get a pair of things here? How many frequencies are present in all this ringing? What are they caused by? So that's what we want to understand. You can understand more of all of this by looking at the spectrum, although the spectrum and the impulse response are complementary. If you look at the magnitude response, those are the same curves. A couple things stand out here also, just at first glance. Left ear is well above the right ear response, at least above 700 hertz or so. We're getting a good 6-8 dB difference between the two. Well, that's the ILD. Notice that at low frequencies, they're both heading down. We didn't go down to DC. If you'd gone all the way down to 0 frequency, you would get 0 dB. Because, why? Because at very low frequencies, the transmission to the free field is exactly the same as what you'd get at the eardrum. There is no difference between the two. So I have to back. I'm hesitating or stammering a little bit here, because in fact, if you get into very close ranges, if you get very close, there is a big low frequency difference between the two because the 1/R is different. But at distances beyond a meter, these things basically come down to 0 dB. Now you see a tendency to rise, right? This is coming up, gets up around close to 10 dB, and then it dips, and then a big boost here. Here's that question was asked earlier about how much gain you can get from the pinna. Well, you're getting, at that point, 20 dB gain, right? Factor of 10. That's quite significant. Then you have these big notches in here. Here's one, here's another one, and here's some peaks. And there's always a question about the physical interpretation of this. The most obvious interpretation, you see a peak like that, you say, oh, it's a resonance, right? It doesn't have to be. It can come from these notch filter effects. It can just be a rebound from the notch that came in here. So we want to understand it. Now, what makes all of this hard is that I'm showing this at one azimuth in elevation, right? And you've got hundreds of azimuths in elevation, so you've got families of these curves. I'm just going to show you one to give you a rough idea of the kind of variation to expect. This is a family of curves for the sound going around in the horizontal plane. Okay? We're looking in all cases at the right ear. Okay? So I'm over here at the right ear. When the azimuth angle is 90 degrees, that means the sound is blasting directly, almost directly in the ear. The ears are actually set back a little bit. People's ears are back about 10 degrees. But basically, you're blasting it into the right ear. And sure enough, when the sound is blasting in, that's when you get really the biggest peak that occurs. If you move around to minus 90 degrees, minus 90, it's on the opposite side of the head, right? So that's where you would expect the lowest response. And in general, it is, although in fact, there are even things that dip down lower. We're going to see that later. Around somewhere here in the back, you actually get even a lower response. And some features stay pretty constant, like the frequency of this ridge here. That frequency is not moving as we go around. That is a real cue for a resonance. If you have a resonance occurring, the frequency of the resonance doesn't matter as to where you put the source. The degree to which the resonance is excited may change, but not the frequency isn't going to change. The frequency is determined by the geometrical dimensions. Other things move around. That notch wanders some, although this looks pretty constant also. Often you see these notches move around, shift around in frequency. Those are interference effects. Okay, well, question?
So far the discussion has been of a static head fixed in space and a sound off here, but a characteristic of this system is that it's active. The head moves,
right,
and it moves in responses to the sound
right.
it hears. Is there a line of analysis that looks at how people choose to move their head to resolve?
Yeah, that's a very important question. I'll repeat. It has to do with the fact that I've been talking all about static cues. And in fact, dynamic cues are very important. Yes, people have done a lot of study on motion of sounds, and you're talking about strategies of how you decide to look around. There's been some work on that. Let me put it in my perspective. If we really want to build a good system to synthesize sound, then we definitely want to include one more element I haven't talked about here, which is a head tracker. And we do. You put a head tracker in the head, so you move your head, we can sense that, and within about 10 milliseconds, we can change the HRTF. So if I'm looking straight ahead, I'm getting roughly the same sound in both ears. If I suddenly move my head around here, now I want to introduce that time delay and head shadow and all those things. I want the different HRTF. If I do not, if I synthesize a sound and I don't dynamically modify it with head motion, then what happens, of course, is the whole sound field tends to move with you, right? If you hear everything move together. And it actually has a very, very bad effect on sounds in the center. Because if a sound is coming directly at you, then basically it's the same sound in each ear. If you move your head around and you don't do head tracking, then it continues to be the same sound in each ear, right? Now ask yourself, where could a sound source possibly be if no matter where I move my head, it's always the same in each ear? And there's only one place it can be, inside your head. And where do you think you hear it? Inside your head. And that's a shortcoming of a lot of spatial sound systems that do not employ head tracking, which is sounds in the middle always seem either very close or inside the head. You just cannot push them out. When you put on head tracking, it all changes. With a good head tracker, this comes back also to the question of, I'm glad you asked this question, a great question. Why do we care so much about the customization? I said front-back confusion reduction and so on, things like that. There's another reason. Suppose you're a small person, you're a child, and you listen to a synthesized sound from a big head. Well, you move your head around, it's going to give you're going to get much bigger inaural time delays than you should. And so the result is that sound source, that virtual source, instead of saying place and space, will actually move contrary to your head. Or vice versa, if you have a large head and use a small HRTF, if you have a really large head, you move your head, you don't get any noticeable sound. The sound moves with you, right? That's actually a very sensitive way to test out how well things are working. If you move your head like this and the sound stays stationary, it's matched to your head. If the sound moves with your head, you don't have the right head size. Okay. Well, I want to shift at this point, before I run out of time, to looking at models. How can we take something that looks as complicated as this and faithfully model it? Let me look at the simplest reasonable model, which is one that's also very well understood and it's very old. It's the spherical head model. It's still worthwhile looking at in the year 2000, 100 years after Rayleigh did this analysis. What's really nice about the model is its simplicity. You have only one parameter, the radius of the sphere. Right? That's the only thing you have to know to analyze things. So here we have a point sound source at some distance r away from the center. And now I'm going to confuse everybody, but forgive me. I'm using theta now as the angle of incidence, which is not quite the same as the azimuth, but it's related. What I'm measuring is the angle between where the sound source is and what I'll call the observation point. The observation point will typically be an ear, right? So think of theta as the angle between a ray to the sound source and the ear. So in the horizontal plane, that's sort of the azimuth. When you get up here, it's that wedge angle that we're talking about. Okay. Well, there are you can solve the wave equation in this case by classical methods, separation of variables in an infinite series solution. And I'm certainly not going to run through the math of that. I'm not going to do any more than throw up this one slide that says we can calculate a transfer function for the sphere. And this head-related transfer function has only three variables, rho, mu, and theta. Rho is a normalized range. It's the range divided by the head radius. That's all that matters. For frequency, mu is a frequency, a normalized frequency. It's the Ka. It's the it's the frequency. It has to do with the time it takes sound to go once around the head. The period, the ratio of the time once around the head to the period is the frequency we're talking about here. And the angle of incidence. If you know those three quantities, you can calculate the transfer function. It's an infinite series with Legendre polynomials and spherical Hankel functions, but it actually is not that hard to compute. I have a MATLAB program that calculates it for anybody who wants to do it. So you get it for all distances and all azimuth angles. Let's take a look at what that produces as a result in the frequency domain. And by the way, Rayleigh's solution is a frequency domain solution. It assumes the e to the j omega t type of sinusoidal source. So if you look at the magnitude of that transfer function calculated, this is what you get. It's kind of interesting. Let's look at it a second. This is a family of curves, normalized frequency on this axis, and this angle of incidence for each curve. One thing you notice right away is they all go to 0 dB at low enough frequencies, right? That's what you would expect. And again, this is source at infinity. If you bring the source up closer, that's no longer true. These curves split apart at low frequencies. But for a distant source, that's what happens. Look at the top, the 0 degree curve. Somewhere around 1 here on this normalized frequency scale, it's up 3 dB, and it gets up to a maximum of 6 dB. You get a 6 dB gain when the sound is blasting right at the ear. Where does that come from? Well, it's a standard reflection thing. You've got a wave. If I had a wave coming against a wall, bouncing off, you can think of that as an image source. The two come together. At the point where they come together, they double in amplitude. Okay? But the doubling in amplitude only occurs at high frequencies where the wavelength is small compared to the head size. At low frequencies, you don't get that doubling in amplitude. If you move out in azimuth, somewhere around 100 degrees, the response becomes pretty flat, which is kind of nice. That's about where your ears are. In other words, when you're looking directly at a sound source, that's when you're sort of getting the flattest frequency response. If you turn your head around this way, you pick up a 6 dB boost, but it boosts the highs. Right? As you move around to the shadowed side, the most attenuation is occurring somewhere around 150, 160 degrees, and then it starts pulling up. At 180 degrees, we see a rise again, getting an almost flat response. So that's that bright spot that people argued about as to whether did it really exist or was that just a mathematical artifact. If you look in general at this, these curves, there are all these ripples, interference ripples. People worry a lot about that and what causes them. And it's not too hard to explain what causes. I'll explain what causes that in a minute. But if you ignore all the up and down ripples here, you can say, well, this looks like at some point it's dropping off at the most. The steepest slope here is about 6 dB per octave. So you can, or 20 dB per decade, you can model that as a simple single pole filter. In fact, that's what we do. Here's a very simple filter. It has in the frequency domain, it has a single pole that's fixed. We keep it fixed at mu equals 1/2 for the corner frequency. And then the zero shifts. The zero moves with azimuth. And here's a family of curves you get out of this model. And they look pretty much like the curves over here, except they don't have any of those ripples in them. Do you hear all those ripples? Is it important to faithfully get all that interference stuff? Answer is virtually never. There's some very special cases where you can detect the differences, but from an auditory standpoint, it's not all that important. So here's a very primitive, simple-minded first-year signal processing for electrical engineers pole zero model does a good fit to head shadow. But what about time delay? That's frequency response. What about the temporal part, the phase part of the spectrum? If you look at the impulse responses, this is computed by just doing an inverse transform on Rayleigh's solution, okay? And because the phase information is all in the solution, what you see for 0 degrees incidence, sound coming right at you, that's when you get the biggest pulse and you get it soonest. 90 degrees away, you get a big time delay and you get a reduced response. So you're seeing the right behavior. What happens as you move continuously around the head? Go all the way around. Here's a family of curves that shows what you get for an impulse response. So I think this is kind of interesting. The curve at the very bottom here, that's the 0 degrees angle of incidence, right? Directly blasting in. Now as you move the sound away from the ear, it takes longer and longer. You can see the longer length of time for it to come. It gets weaker, lower in amplitude. Head shadow is starting to occur. At 180, you're diametrically opposite, right? And look at this little blip that occurs. And now you can understand exactly why, because as you continue on around, to first approximation you can think of 2 waves going around the head. And so if the sound source is over here, and I'm looking at this ear, the main wave comes around the front of the head, and I get that. But a little bit later, a wave around the back of the head passes by, right? And when I'm diametrically opposite, these 2 waves come together in phase, and they build up this bright spot. The bright spot is occurring, however, when that sound is on the opposite side of the ear. And at that point, the sound level is really dominated by the ipsilateral ear. The contralateral ear isn't that sensitive to things. So if you fail, like in our model, in our simple model, we fail to include that bright spot. It's very hard to hear its absence. You can take the time delays that we get from this model, you can calculate them by, well, for example, we took a 15% rise time definition. We said when this goes up 15% of its peak, that defines an onset time. And this is from calculated from the Rayleigh's infinite series solution. Okay. You can also use an elementary ray tracing argument. A man named Woodworth did this 50 years ago. Okay. Said, look, sound is coming, it goes directly to the ipsilateral ear. Well, if the ear is, let's see, if the sound is over here, it reaches the ipsilateral ear with this much of a distance before it reaches the center of the head, right, a sine theta. And on the contralateral side, it goes tangent and then follows sort of propagates along the head, and so you have a theta path length. And from this geometry, you can calculate an interaural time difference. It's an oversimplification in some ways, and yet it's remarkable how well it fits the exact solution. This shows the arrival time as a function of the angle of incidence. And you can see the solid curve is Woodworth's formula. The circles are calculated from the Rayleigh solution. The fact that those circles are not perfectly along here is probably due to numerical errors in our infinite series, not to the theory. So it's a very excellent fit. So all this, you put it together, you come up with the world's simplest HRTF model. Okay? There it is. You say, take your sound source, run it through that single pole, single zero filter to get the head shadow effects, run it through the time delays that were calculated by Woodworth's formula. You get a left and right signal, run it into earphones, and you will, voila, get 3D sound, right? No. No, it's not quite that good. What can we say about this model? Well, let's get its good points first. Here's the good news. Good news. Only one parameter. The only thing you have to know is the head radius. And so we've done, in fact, simple regression analyses. If you measure the height, width, and depth of your head, we can get you a very good head radius calculation. You get a very well-focused sound. If you didn't have both the time delay and the head shadow, if you had only one of the two, it blurs or splits the images. For example, if the only thing you do is make it louder in one ear and softer than the other, it certainly tends to get a sound that's over toward the ear where it's louder. But if you listen carefully, you often hear two sounds. You hear the sound there, and you hear a sound in the center of your head. It's because you haven't got the right time delay that goes along with it. So putting those two together gives you a well-focused sound. If you adjust the azimuth angle, boy, you smoothly move it left and right. It's great. Of course, you don't get anything up and down. That's not part of the model, right? And most people hear it as being elevated, or to be more specific, when the sound is supposed to be straight ahead, you tend to hear it up here somewhere. And as you move it over to the right ear, it comes down to the right ear, and up to the left ear, it goes down there. So you get kind of a trajectory through the head. If you use a head tracker, it's remarkably good. I've done experiments in our lab with that, put people on with the headphones and the spherical head model. You walk around. You get a pretty nicely externalized sound from it, as if the sound is really out of your head. Not as far as it should be, but certainly not at infinity. The model says the source is infinity. Well, you hear it maybe a couple feet out. Very little front-back confusion. In fact, it's really remarkable because we do things where the sound is supposed to be here, and the person walks past it. You hear it go right behind you, and yet the model had nothing in it to give front-back. It was totally ambiguous, but that dynamic cue resolves it. Now, if you don't use a head tracker, it is a loser. The sounds are always internalized. It's always in the head. And for most people, it seems to be in back. I don't know why, but people say it's because you don't have absent the visual cues, you can't see it, you throw it in back. I don't think that's the full answer, but anyway, that's what happens. Okay, well, gee, what do you expect of a spherical model? That's so primitive compared to everything else. What are we leaving out? We're leaving out a lot of things. In particular, we're leaving out the torso. So what can the torso do for you? Well, the torso can provide some of an elevation cue. Not a very strong one, let me say at the outset, but it's nevertheless there. Because if you have a sound source reach the ear directly, there will be a reflection, a specular reflection off the torso that comes a little later. And so that leads to a new simple model which says, take your incoming sound, run it through the head model, but then also attenuate it because you get about a 30% reflection off the body, and put in that torso delay, and then run it to a slightly different head model because the angles are going to be different coming in, and add those together, and that'll be your next most, that's level 0, level 1 approximation to an HRTF.
So this is what we would use if we didn't have peanuts.
That's right. If you did not have a pinna, if all you had was a torso and that's all you had to judge elevation, then this would approximate you, right? It turns out that the most important part of this is the binaural differences. That this time delay, this delta t here, is a function not only of elevation but also of azimuth. It's different for the bounces to the two ears, and it's that difference signal that gives you the cue. And it turns out to be mostly a low-frequency cue, below 3 kilohertz or so, where it shows up as being important. It does not solve the problem. So we can say, well, the model now We've gone up to 5 parameters, by the way. We now have not only the 3 parameters for the ellipse, but the head is definitely moved forward and above the ellipse, so you need those 5 measurements. That's still easily customized. We've done that. We do get an elevation cue, but it's only one part of the story. Well, that brings us to the main part of the story. Ears. Gee, you look at ears, and at first glance, they're all different. And in fact, they've been used for biometrics, right? You can go down to NIST or other places and see biometrics conferences where one of the things they'll do is try to identify people by ear shape, right? So it's a fingerprint of sorts. However, as different as they all look, it turns out remarkably, again, with some exceptions, there are people who have, congenital defects or something, but basically, most people have the same cartilage structures. And there are nice Latin names that go with all of it that don't matter much to me. But there are 2 major cavities that are very important. There's this lower one here. It's called the concha. It's divided by this ridge into the cymba concha and the cavum concha. But I'll call the whole thing the concha. The concha is the major lower cavity. And then there's a major upper cavity, the fossa. That's not as deep, but it's also important. Those are the key structures, and they have quite an effect on high frequencies. To understand it, there are 2 explanations that are given, and they're both right, even though they've been subject to dispute. The first person to focus on the pinna was Bateau, and he used a time domain argument, which I like, which most psychologists don't like. It says, well, look, the sound comes directly to the ear canal. The sound comes to the concha, hits that wall, and bounces back a little bit later. You've got a delta t in there. It's small. It might be 50 to 100 microseconds, 200 microseconds at most. But it's definitely puts notches into the spectrum at audible frequencies, anywhere between 6 and 18 kilohertz. So, and the important point is that if you move the source around the head, you change that time delay. So you change where that notch in the spectrum occurs. I think where part of the controversy came from was that Bateau liked to think of that as an echo. He'd say, oh, look, you're getting an echo off of the back wall, and so you're just hearing these echoes. And that is actually, of course, not true. I mean, you cannot hear anything like an echo until you have time delays more than, I don't know, 10, 20 milliseconds. So poor choice of words, but the concept is still correct. Edgar Shaw in Canada did some very painstaking studies over a series of years on the resonances of these cavities. He found, for example, there's always a lowest frequency resonance here, which is in fact a longitudinal resonance. It's sound going in and out of the concha. And then the next resonance you hit is one that's on a vertical axis here. Here's a mode. And this resonant mode is a transverse mode. And these show up quite differently in terms of the impulse responses. In an impulse response, if you have a transverse mode like this, where you can think of the sound echoing back and forth, if I can dare use the word echo, if you think of it reflecting back and forth across here, every reflection has the same polarity. If you look at the impulse response, you'll see plus, 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 right? Whereas in a longitudinal resonance, the sound goes in, reflects off, the same polarity, comes out, hits the radiation out into the air. The impedance is now very different. Instead of being a high impedance that you had at the inner reflection, it's now a very low impedance. It results in an inverted polarity pulse. It's like, for the double E's here, it's like a transmission line. You short circuit or open circuit at the end. One way you get reflection one polarity, the other the other. So when you see those negative undershoots, those are coming from this kind of a longitudinal resonance. The positive ones are the transverse. So you have these modes, and the other key thing is that the degree to which any of these modes gets excited depends on the direction. So if I move around different elevations, when the sound is coming either from above or below, I'm going to tend to excite this mode. But if I have a sound coming this way, I tend to excite that mode. So the residues in the poles, the strength of the excitation, depends on position. So now we have, well, Well, actually, what I would like to do, I brought some slides because I'd like to show you some data. It helps to see some high-resolution pictures of all of this, and the best ones I have are on slides. So why don't we turn on the projector here? Okay. Up to high, good. And could we lower the lights a bit so this can be seen? And I'm going to step down into the pit here before I fall into it. See, can these lights come down? They're working on it, okay. I can talk about this while they're getting the lights down. What you're seeing here is a picture of our lab setup. That's actually Kimar, the dummy sitting in there, although usually a subject is seated in the center. What we have is a hoop. This is actually circular, this blue hoop going around here, and it's driven by a motor. The axis is through the ears. We find it very convenient to use the interaural axis rather than the vertical polar axis for our coordinates. So we swing that hoop around the subject from down fairly low to down and back, and all along the hoop we place loudspeakers. We actually repeat this process. We move the speakers into different positions and then go through the process several times to get roughly a 5-degree accuracy in both azimuth and elevation angles here. 5 degrees is considerably higher resolution than most people use. I know why. It is tedious. It takes 3 hours to go through and measure a full HRTF this way. But it has a big advantage that you can take a look at the data now and see things that are changing spatially. But basically, we're sampling in space, right? We're sampling in azimuth and elevation. I think most past studies have sampled above the Nyquist frequency. They've been missing features just because of coarse spatial sampling. If you look at the next slide. The next slide shows that series of curves. I guess I'm the one that controls that. Okay, this is the spherical head solution, or should be. There we are. I put it up here to remind you of this because I want to show you a different way of looking at the same data. Let me remind you what you're seeing. For the spherical head, here we have frequency, we have response amplitude. We're looking for various azimuth angles, and you see that 0 degrees, we get that 6 dB boost. But as we move around the back, it drops, there are ripples, and it comes up to the 180, right? I'd like to show you the same thing, same information, but represented as an image, where brightness will be used to get the dB values, and then I'm going to use the 2-dimensional axes to give you frequency and the incidence angle. So here's the same data. Here's frequency running down this axis, right, low to high frequency. This is that angle of incidence. And now anything that's bright, that's large number of dB. So in general, just looking at this, you see this whole area is bright. Right? So anywhere around 0 degrees azimuth blasting right into the ear, that's where you're getting your 6 dB at high frequencies. If you get down to lower frequencies, it's hard to see in this. That's one of the disadvantages of images. Images are not good for getting absolute dB values. They're good for looking at trends. At low frequencies, this should be heading towards 0 dB, but there isn't that much difference between 6 and 0 brightness scale. If you move over on the right-hand side, now you're in the shadowed area of the head. So this is the contralateral side. It's generally darker, except right through that zone, there's the bright spot showing up. And then all of those ripples that appeared in the curves are, of course, showing up as this kind of streaky fan-shaped thing here. Okay, what I want to do is compare that sphere to what happens when you measure an actual person. Well, it's a Kimar, but Kimar is sort of I think of Kimar as a person these days. So here's Kimar's measured HRTF. Now, it's a little blockier. You see this, the squares and rectangles, but you see the same general trend. That is to say, bright all on this side, dark all on this side. Here's some of those kind of sort of ripply patterns, not nearly as well defined. Here's a bright spot showing up in here. So there are some features that are matching the spherical head model. But there's a lot of stuff here that you never would see in the spherical head model. What's all this real dark stuff running through here? And how come the bright spots appearing out around other places? Well, those are all pinna effects. There are also torso effects that are not seen on this slide. This is an impulse response, and it's an impulse response in the same kind of representation as an image. I know that there is, okay, let's see. The first thing, this is a simple one because I've removed the pinna. That's one thing that's nice about Kimar is you can take the pinna off. And so if you do that, you simplify the image considerably. As an impulse response, this is now time running down this direction. So if I come down, let's say I take the 50-degree azimuth angle here. At 50 degrees azimuth, I come down that column. At the top, you're not getting anything, and then suddenly get that bright ridge. This whole upper bright ridge, that's the initial impulse hitting. And then there's something that follows it, and it fades out. And then you get this second weaker ridge that appears along here, and then it finally disappears, right? You look at the whole thing, you say, well, look at this part of the curve here. That's obviously what's going to be the time delay, right? As I move around in azimuth, if I get out, 90 degrees is where I get, or 100 degrees is where I get the shortest arrival time. That's right in. As I move the sound source back around the back of the head and over toward the other ear, toward the left ear, it takes longer and longer. And then you get to this spot. There's the bright spot right there. And then it swings up as the wave picks up from the other side of the head. So you can see those features nicely. What about this stuff here, which is the major other thing that's showing up? That you can attribute entirely to the torso. That is the torso reflection coming in. It's not, the time delay here is not changing very much with azimuth. As I swing around in azimuth, there's some change in time delay. Particularly you get around the contralateral side, it's getting complicated because the torso reflection is going around the neck and it's messy. But basically it's not giving you an azimuth cue. Yes?
Since Kimar's head is hollow, is there stuff that comes in from one side that actually bursts through the head?
Well, the answer is yes, there is, but it's about 50 to 60 dB down. For all practical purposes, you can forget those body transmission things. It really is not important. Okay, what happens if I put the pinna onto Kimar? Well, the next slide shows what happens. For one thing, it does obscure that torso reflection, although it's still there. But you see all this other stuff appears. Notice how that initial pulse has split now over here into two clear pulses. That's a direct pulse and a reflection off the concha. We have other patterns that are appearing. I'm not going to go into all of them. I'll just say right now that, yep, putting the pinna on definitely complicates things. Those resonances are showing up with the repeated rows of ridges. So here you can compare, if you want, the response without the pinna and the response with the pinna. Here we're going around the median plane. And I have one slide that has this orientation. It makes it a bit more clear. Now it's an impulse response, time running out along this axis. This bright ridge here closest, that's your initial impulse coming in. Here's the torso reflection coming in. And you can get an idea of where are the elevation cues coming from as we go around. You can see some of it here. It's not everything. In particular, you can get an idea of front-back. If we were symmetric front-back, then this would be mirror image, but it's clearly not. It's quite different here than it is here. These two ridges sort of blend together, and one fades out, and this dark notch area thins out, and various things do change. And those are all physical sources of elevation cues. In fact, those are the main monaural cues in the time domain. This is the same data, only plotted differently. In fact, well, it's different in two ways. It's plotted differently, and I've moved the source off the median plane, so now you can see the difference between the near ear and the far ear, the ipsilateral and contralateral. So the ipsilateral ear, that initial impulse comes first. Here's time running down here, elevation, so we're going from down below, straight ahead, up above, in back, down below again, right? So on the ipsilateral ear, you get the initial pulse coming in. No matter where I am going around that hoop, right? I'm moving the hoop around that elevation angle. No matter where I go, on the ipsilateral side, it's taking the same time because I have the ear right on the axis of the hoop. So that's why this initial impulse occurs at exactly the same time along here. If you shift over to the contralateral side, then it's sort of constant, but there's a little dip here when you're near overhead, right? It's not really a constant time. And the reason for that is twofold. One is that the ears are down and back, and the other one is that the head is not a sphere. The head is a shorter dimension around the front usually than over the top, so there's a longer time delay for the sound that comes over the top of the head. You see the concha reflections coming in here. You see this stuff here? It's faint. Here's the first one. It's kind of a U shape. That's the torso reflection showing through, okay? With the pinna present. If you take the pinna off, that really stands out as being much more clear. The contralateral ear is sort of a mess. You do see the bright spot, and that kind of in fact, see how this wave continues on through here. But you might begin to wonder, is Duda hallucinating? You know, he's telling me, see that, see that? Well, take it on faith, it really is there. Okay. So we can identify then a bunch of features. On the ipsilateral side, the main pulse, the pinna reflection, the torso reflections, the pinna resonances rippling through here. On the contralateral side, you can see the bright spot path around the two sides of the head, and the difference between these giving you the time delay. Okay. I should, no. If you remove the pinna, and now I'm back in the frequency domain, just to confuse you. I've gone back to the frequency domain. Here on a log frequency scale, what you're seeing, all these arches, all of this structure in here is coming from torso alone. It's the comb filter pattern produced from that echo off the torso. If you put the pinna back on, which is the last of these slides, let's take a minute to look at this one. This is the spectrum now. Pinna present, everything present on Kimar. This dark arch and all of these arches that you see running through here are all torso reflections. The bright spot, the bright region or bright zone you're seeing over here, that's all the lowest resonant mode from the concha. Okay? Resonances in general, if you talk about concha or fossa, or pinna resonances, those resonances will show up as horizontal streaks in here. There'll be frequencies as you go across that nothing changes with elevation. Right? So there's one right there, goes right across the image. So there's a resonance up around 8 kilohertz. There's another resonance here going right across the image. Okay? You'll see notches that move. Look at, there's a notch here, a notch here, a notch here. This isn't so obvious in front, but it's in fact moving with elevation. Those are being caused by that time delay from the first wave to hit the ear canal to the reflection off the back of the concha. And I think that's the last of the slides. Any questions on this stuff? I want to know when lunch is. Yes, we also have measurements without the torso, and what happens is just what you'd expect. All of these bands disappear, and I don't have it with me, but we have the data. Okay, so that's with and without pinna, and I think that's the end. Good. Okay, let's see, should let that cool off a little. I'm almost finished. Get my projector back. Okay. Well, this suggests an obvious next approximation, level 2 approximation, to say, look, we can approximate an HRTF by having a head shadow model and head delay and a torso model for that reflection, and then all we really have to do is add a pinna model of some kind. We know the head model is easy. The head model is just to put in that single pole zero filter, time delay with Woodward's formula. Torso, a reflection, you can make that reflection actually a constant. It's not really, if you measure it, you find it does change with azimuth and elevation, but we've done listening experiments and it doesn't matter much. Typically around a 30 to 40% number here, 0.3, 0.4 works fine. A time delay you can calculate from an ellipsoidal model. You can measure it. They both give about the same results. That's easy. Here's where the problem is. The form of the model is clear for the pinna. At least we think the simple form is clear. From the physical argument that says, look, there's a direct sound that gets to the ear canal. You can follow it with an ear canal resonance if you want. That's a fixed resonator. Then we have these different resonant modes, and they each have their own strengths or residues. The residues will vary with elevation and with azimuth also, but elevation is the key variable. These time delays, very important, they vary with elevation. But the resonators here are fixed poles, right? You don't have to change that. Making it work correctly and fitting it to the data, it's been trickier than we thought. And initially, it looks like a very simple system identification problem, right? You've got a model, some parameters, you've got data, you just have to match things. Matching these time delays turns out to be a numerically very bad problem. Our results are mixed on making this work, which brings me to my conclusions, which you've seen before. I guess I don't, let me repeat them. That these HRTFs do capture the cues. If you listen to sound synthesized through them, you get a nice spatial sense of where everything is. And the models do explain the basic features and behavior of them, and the major components we need are head, pin, and torso. And we can fit these models to data, and no problem with the head and the torso. But the challenge for the next few years is to do this for the pin. And at this point, I'll stop with that. Any questions? Yes?
So you talking primarily about the synthesis side. On the recognition side, where you have some sound and you want to know where it is, can you make use of some of the same models?
Sure. Dr. Netty here has actually done that. And I've done some of that too in my students. There are a lot of ways that one can approach it. The HRTF is only, again, part of what you want to have. The simplest thing to do, which a lot of people have done, is to say, take a sound that comes in, particularly this is nice for the binaural things, take some segment like 30 milliseconds or some length of time, get the transform in the right ear and the left ear, take the ratio of the spectra. The ratio of the spectra, the source spectra should drop out, and you ought to get the ratio of the head transfer functions, right and left, right? And now do a best match, do a least squares match against what you get in a table, and you say, oh, look at that, azimuth 30 degrees, elevation 46, it's a perfect match. I know where the sound's coming from. It works wonderfully well with one sound source in an anechoic chamber. It's so good you wouldn't believe it. You know, 1 degree accuracy, much better than people can do. Put it in a normal room, even one source in a normal room with room reflections. Azimuth, often confused, front, back, things confused. Elevation, hopeless, just hopeless. Number of things have been done to improve performance. I had a student do a nice thesis in which he weighted the he would make these estimates at multiple times, and he, at any given time he would look to see, he would do independent ITD measurements and ILD measurements at each channel, and he'd look for consistency. When do we get a consistent pattern across channels? He would look for times when there was a rapid buildup, typically vowel onsets. You look at when you're getting 5 dB or something per cycle of buildup of energy. That was a good time to grab. He was able to do quite well in a normal room with several different people, several different speakers, not very well with more than one person talking at the same time. It gets you into the cocktail party problem and other things. It's a great problem, but not as easy as the one I'm working on. Yes? Yes. Yeah, repeat the question. You're talking now about elevation, right? But if you look at that, if you look at those frequency responses, I probably should see if I can, well, I won't put it back up again. there is a first notch that occurs. And that's the one that's caused by the interference between the direct sound and the reflection off the back of the concha. And that notch, the frequency at which it occurs, moves as you move in elevation. And there was a man named Tony Watkins who did wrote a paper back 12 years ago or so on using that single cue. And it's not a bad cue. It's not the whole story, however. Those other modes, those higher frequency resonances, you want to have them come in and fade out properly with elevation also. This is one of the frustrations in doing this kind of research. Even a simple spherical head model gives you, part of it. Each time you add, you have to ask the question, is this perceptually important? Is it necessary? What's the simplest thing I can get by with? And what's hard to answer, all those things require psychoacoustic tests. And it turns out, because they're so time-consuming and painful to do these tests properly, people tend to short-circuit things by saying, well, we'll test at these 4 points in the horizontal plane and these 4 points in the median plane, and we're done. And then they completely overlook things like that torso cue that occurs off at 45 degrees. And it's difficult to say what's necessary. I agree with you that the pin and notch, if you wanted to put one simple, if you wanted to take the spherical head model, and the only thing you want to do is to bring that thing down in front, right? There's a tendency to hear the virtual source as being elevated when it's in front. Putting in a notch will generally pull it down. So there's an engineering art to finding the right combination of things you want in the model. Question?
So you generate the sound that's supposed to sound like it's coming to a place, and based on the reflection and whatever else. But when you put the headphones on, does it matter if the factor has to go through the antenna again, or are the headphones?
Yes, good question. In fact, there's a bigger question. Let me repeat the question, which is, if you're going to listen to this through headphones, the headphones are also exciting pinna resonances and ear canal resonances. And so what do you do about that? And do you have to use headphones? That's another question which I had expected to get. Let me answer your question first. We always do a headphone compensation. We have a procedure whereby we put a little probe tube microphone in the ear and you put the headphones on and we measure that transfer function. It's a fixed transfer function. We try to then compensate for those resonances. It's pretty good, except some of those are actually pretty sensitive to the headphone position. If the headphone moves around on your head, you're trying to cancel out some resonance, you can get into trouble. Fortunately, for me, it's not a big problem because those resonances are all at frequencies I can't hear anymore. But on the other hand, I hear so badly, I shouldn't even spend any money on a spatial sound system. The headphone compensation is something that is a problem. It's an area I think can be, what should I say? I think it's a good topic for what we're doing right now on the boundary element methods. I see that one of my colleagues from Maryland here. The numerical simulation should let us answer a lot of those questions on what to do about headphones. But it's an effect you should compensate for. In terms of do you have to use headphones, because there are a lot of applications where people won't put up with headphones. The answer is, well, you don't have to. In fact, a lot of systems use loudspeakers. There's a very nice system at the University of Southampton called the stereo dipole that has speakers very close together, 10-degree angle. They use what's called crosstalk cancellation to get rid of the headphone effect. And it has only two problems. One problem is that you have a sweet spot. If you move very far away from the zone, it all falls apart. Now, in theory, you might be able to track people's motions. Right? If you're going to wear a head tracker anyway, or if you have even video cameras, you track the motion and then adjust the crosstalk cancellation. You could certainly enlarge the sweet spot that way. But it means for an audience. I have a problem when I give a talk like this. Fred asked me earlier if we're going to hear some sounds. Gee, how can you give a talk about sounds and not play a single sound? And the reason is that it's very hard for me to demo any of these things. If I get loudspeakers, I have to have everybody lined up in the same spot. If I start handing out headphones, which I've done, I can do that for 8 or 10 people, but it's unmanageable. So it makes demos hard, but for small groups, no problem. On the speaker side of things, the other problem I was going to mention was it's hard with speakers to really get the sound to appear to be coming from behind you or very close. Headphones have the big advantage, if you have an application that needs it, that you can get a wonderful impression of somebody whispering in your ear or moving far off into the distance. You get that dimension of sound is nicely controlled with headphones. Yes?
What are your thoughts on synthesizing particular kinds of sounds? So let's, if we're doing speech, then have you thought about combining it with
Okay, yes, in fact, well, actually, your question reminds me of an earlier conversation we had today. Mostly what I'm talking about would have worked with any sound source. I don't care what the sound source is. If you're going to insist on playing a sine wave and run it through these models, well, it'll produce a sine wave on both the left and right ear with some amplitude and phase. You won't have any idea of where it is because sine waves are almost impossible to localize. There's a famous experiment. How many people have heard of the Franson effect? Anybody know the Franson effect? Let me tell you, it's a simple experiment you can do. That you guys could program this up this afternoon. Take two loudspeakers, put them wherever you want, a few feet apart, 10 feet apart. You take a sine wave, you have it come on in amplitude, build up with about a 50 millisecond onset to its full amplitude, except that what you do is that you put only the onset part through one speaker. Through the other speaker, as this speaker fades out, this speaker fades in. So the steady state is coming out over here, the onset was coming out over here. You play that sound, boo, you ask, and it continues by you say, boo, and right, the tone keeps going. You ask people, where's that sound coming from? They point to where the onset was. Okay? You say, walk around and see if you can find it. They walk around. Now, when you start walking around a room with a sine wave, you have standing waves. You walk into nodes, you walk into antinodes. You're very confused. You say, that sounds still. I hear it from... What's going on is that you heard the initial transient and you correctly localized from the initial arrival time. And from then on, you were getting such weak cues, you didn't have any idea of where it was, but your brain says, well, I know it was coming from there. So I exaggerate the experiment a little bit. You got to do this somewhere around a frequency of 800 hertz or so. If you go very much lower, very much higher, very much lower, the standing wave pattern is different, very much higher, other things happen. But nevertheless, the point of all this is some sounds you can localize much better than others. How about speech? How well can you localize speech? Quite well, even though the high frequency end isn't terrific, right? You're not getting a lot of energy above 4 or 5 kilohertz, but you do get these initial onsets that are very helpful. I think I mentioned to you earlier this morning that I'm interested in a speech synthesizer which would be sensitive to range, so that if I'm very close, if I want to synthesize an effect that sounds like a person in a conversation with you, it sounds like they're getting close to you and talking to you, they come in or they back away. When they get up, I don't want it to be when they're right up to your ear that they're still talking this way, and you would move away from them, right? I want them to clap their voice and whisper, right? Or I want them to shout when they're far away. So I'd be interested in synthesizers that would do that. That would be a connection between the synthesizer and the spatial effects. Question? So the question is, could we develop some prosthetic device, something that we could use to improve our localization ability? Right. Yeah, I think the answer is yes, it can be done. In fact, there's an experiment that was done was kind of funny. Some people, I can't remember the names now, some people in the Netherlands who built some very large pinna, plastic pinna that were attached to the head. And you get people to wear these things. And at first, they have things sound strange, and they do have a hard time learning where things are coming from. But you adapt to it. It takes, as I remember, it takes about a day to get used to it, and after that, you are able to localize and in fact get some improvement in spatial localization. The remarkable part of this story, many of you have heard, I'm sure, of the experiments, similar ones with glasses, right? You put on these prisms that turn things upside down, and after a few hours, things look normal again, and you can. I think Joe Montana was throwing footballs with these glasses and was able actually to complete a lot of passes, even though the images were upside down. The funny thing about the visual one is you take these inverting glasses off, and you're all off again, and it takes several hours to get used to it. And for no known reason, with these plastic pinna, you take them off, and right away you're back to normal. So strange.
I think we'll.
Time to call it a day. Thank you very much.